Good evening. You are welcome to chemistry class. Today we'll be looking at the topic that says nitrogen and its compounds. Nitrogen and its compounds. Nitrogen belongs to group 5 in the periodic table. It belongs to group 5 together with some other elements like phosphorus, arsenic, antimony, and bismuth. You can see their chemical symbols written in brackets in front of them like that. And nitrogen, we need to know that it occurs as a free element in the air. When we say free element, it means it is not combined with any other element. And when it occurs as a free element, it exists as N2 gas, that's nitrogen gas. And that is the major constituent of air, the air around us, to the extent that it occupies about 78% by volume of the atmospheric air. So this form of nitrogen in the air is very important because it reduces the activity of oxygen in the area of combustion, respiration, and oxidation. All these are processes that are very important to us in nature, but they must be kept at a reasonable extent. They must not be too high, or else it will result in something negative. Imagine combustion, which is the same thing as burning, is occurring at a very high rate that it is difficult. It is occurring at an uncontrollable rate. You know what calamity that one can cause. So then nitrogen also occur in combination with other elements in crusts, especially as triazonitrate 5 salts of sodium and calcium. That is sodium triazonitrate 5, calcium triazonitrate 5, as well as ammonium salt. For example, ammonium sulfate, ammonium chloride. All these are compounds that contain nitrogen in nature. So nitrogen can also be found in organic matter such as proteins, urea, and vitamin B compounds. So that is the existence of nitrogen in nature as free element and in combination with other elements. Now let's go to laboratory preparation of nitrogen. There are several methods of preparing nitrogen gas in the laboratory. Number one among them is from the atmospheric air. So we know that air is a mixture of gases. Nitrogen is the chief among the constituents of air. We also have carbon dioxide, we have oxygen, we have rare gases, which are also called the noble gases. Those are the group 8 elements or group 0 elements in the periodic table. Now what we do here is we remove other elements, other constituents of the air, mainly carbon dioxide and oxygen. Carbon dioxide is removed using caustic soda, that is sodium hydroxide, while oxygen is removed using heated copper tunnels. Copper tunnels is a granulated form of copper. It will be heated. So in the diagram there, the air will pass through the aspirator bottle originally contains air. So when you run water into heat to push the air forward, the air passes into caustic soda, which is sodium hydroxide, to remove the carbon dioxide there. Then oxygen that is also present in the air will be removed as it enters the copper tunnels segment. So the remaining air will be, the remaining component of the air, which is mainly nitrogen and small quantity of rare gases, which will serve as impurity, can be collected over water. The reason why it is collected over water is because nitrogen is not a soluble gas. The solubility of nitrogen is very low. So, and it is also collected over water using upward delivery. Upward delivery because the gas is less dense than air. So take note of that. Not even for nitrogen gas alone, but for other gases in chemistry as we continue to learn more. So then the second method of preparation of nitrogen, that is by reacting ammonium chloride and sodium dioxynitrate 3, that's NaNO2, reacting the two of them together in the presence of by heating the two of them together to give us ammonium dioxynitrate 3. So it is this ammonium dioxynitrate 3 after being produced that will decompose because of the high temperature in which the reaction takes place to give us nitrogen gas and steam, as you can see in the equation there on the screen. Then this method of nitrogen is by decomposition of ammonium dichromate. So you heat it to decompose. Ammonium dichromate is also known as ammonium heptaoxodichromate 6. That is the IUPAC name of ammonium dichromate. So as you can see in the equation, the nitrogen gas is being given off from the reaction mixture. So number 4, as you can see here, nitrogen gas can also be liberated when ammonia is oxidized by hot copper 2 oxide. So the reaction between ammonia and hot copper 2 oxide gives us nitrogen, as you can see in the equation there in number 4. Then in number 5, we also have the laughing gas there. That's the dinitrogen 1 oxide being passed over red hot copper. So nitrogen will also going to be formed according to that equation, as you can see on the screen there. Then industrial preparation of nitrogen. It is obtained in the industry, that is on a large scale, by fractional distillation of liquid air. A sample of air will be compressed under high pressure into a liquid form. Then fractional distillation will be carried out on it at different boiling point of different mixture, of different constituents of the liquid air. Each component, the component at the respective boiling point will distill out of the mixture. So that is how to get nitrogen on a large scale. Now let's move to the physical properties of nitrogen. Physical properties of nitrogen. It is a colorless, odorless, and tasteless gas. It is slightly less dense than air. We mentioned this one when we're talking about the number 1 method of preparing nitrogen gas in the laboratory. It is less dense than here. So let's do a little deep teaching on how to detect whether a gas is denser than air or less dense than air. Now, what you use here to determine whether, so that you will not need to be cramming every time which one is denser than air, which one is less dense than air. Whenever you want to determine the density of a gas compared to air, you use oxygen as the density of air, as a gas that has the same density as air. The oxygen is almost the same density as that of air. So you now look at the relative molecular mass of the gas and compare with the relative molecular mass of oxygen. The relative molecular mass of oxygen, which is O2, is 16 times 2, which is 32, because the relative atomic mass of oxygen is 16. So 16 times 2 will give you 32. So any gas whose relative molecular mass is less than 32 will most likely to be less dense than air, and any gas whose relative molecular mass is greater than 32 will likely to be denser than air. In fact, most likely to be denser than air. So using this nitrogen that we are talking about as an example, nitrogen is N2. The relative molecular mass will be 14 times 2, because the relative atomic mass of nitrogen is 14. So 14 times 2 will give us 28, which is less than 32. Of course, you can see it's going to be less dense than air. So you can try that particular formula, that particular method to detect the density of other gases in relation to air. So the number 3 point under the physical properties of nitrogen that we have here says that it is slightly soluble in water. The gas is slightly soluble, that is, the solubility of nitrogen in water is very low. It's very low. So let's move on to the chemical properties of nitrogen. Before we talk about the chemical properties of nitrogen one after the other, we need to know that the chemical reactivity of a particular substance must take place with bond breaking. That is, the bond that is holding that chemical substance together must be broken before a chemical reaction can occur. In the case of nitrogen gas N2, it has a triple bond, as you can see on the screen there. That triple bond is very strong to be broken, and that makes nitrogen gas to be very unreactive. So the bond energy for nitrogen gas is high. So to break it, you may need to apply a very high temperature or pressure for that bond to be broken and for a chemical reaction to occur. That is why the chemical properties of nitrogen are very few. Now let's look at number 1 of them. It combines with very electropositive metals like magnesium, calcium, aluminum, and iron to form nitrides. It has to be very electropositive metals because originally the nitrogen itself is not very reactive. So for a chemical reaction to occur with it, it will require another compound or substance that is very reactive. That's why very electropositive metals, because the higher the electropositivity, the higher the reactivity of the metal. So these are the kind of metals that can react with magnesium to give us the nitride. So magnesium is used in that place. These are the kind of substances that can react with nitrogen to give us the nitride. So magnesium is used here as an example to give us magnesium nitride. So this is readily hydrolyzed when warmed with water to give us ammonia gas, as you can see in the equation there on the screen. So let's move on to the next chemical property. It reacts with hydrogen gas. That's a reversible reaction to give us ammonia. That's the major reaction in Haber process for the production of ammonia. Then the chemical property that we have here says that at a very high temperature of about 2000 degrees centigrade, oxygen and nitrogen combine to form nitrogen 2 oxide, as you can see in the equation there. So that's about the chemical properties of nitrogen. So what about the uses? If nitrogen is of no use, then why studying it? So it is used for making some important chemicals like ammonia, cyanide, cyanamide, and carbamide. Carbamide is even a fertilizer. So nitrogen is used for making these important chemicals. It is used as a cooling agent, as a carrier gas in gas chromatography, and it is also used as a preservative to prevent rancidity. Rancidity is a situation where a food item gives offensive odor or offensive taste as a result of the action of certain germs or microorganisms on them. So nitrogen can prevent that because it can be used as a preservative. So the assignment here for the student, they are to give an example of a compound or ion. It can be a compound or ion that contains nitrogen, which the oxidation state of nitrogen is -3, -2, -1, 0, +1, +2, +3, +4, +5. So each must have a compound or an ion where nitrogen has this oxidation state. Whenever you are writing an exam, if they say give, you can give the name or you can write the formula. But if they say name, it is the name you must write. Sodium chloride, for example. Don't write NaCl. But if they say give, you can either choose to write a name or formula. But in this assignment, you have to do both. Write the name, give the formula of any compound or ion that where nitrogen has the oxidation state of each of these. So that is that about the assignment. Now let's move on to the nitrogen cycle. Nitrogen cycle, this one is talking about the continuous circulation of nitrogen in nature, from the atmospheric nitrogen to how nitrogen is being enters plant, from how it's move from plant to animal, from animal back to the soil, or from the plant back to the soil, and from the soil back to the atmospheric nitrogen. So this is all we are talking about in nitrogen cycle, and they have been summarized into certain points which are highlighted below. So let's look at them one by one. As we see on the screen, then the first one says some leguminous plants like beans, peas, and melon, they use the nitrogen in the air by the help of certain bacteria. We call them nitrogen fixing bacteria. There is going to be a reaction in between them from the nitrogen in the air and some chemical substances in the body of plants. They form proteins. So they form proteins, that is plant proteins. Then what about thunderstorm? There's always an electric discharge in form of lightning during thunderstorm. This electric discharge catalyzes a reaction between nitrogen and oxygen in the air to combine. So when they combine, of course, you are going to have oxides of nitrogen, like nitrogen 4 oxide, nitrogen 2 oxide, like that. So this nitrogen, they are washed down by rain, either by dissolution or by direct washing down like that. For example, nitrogen 4 oxide will be washed down by dissolution. It's a soluble gas. It dissolves in water to give triazonitrate 5 acid. It enters the soil. Nitrogen 2 can also enter the soil, but it might not be by dissolution. So all these things, when they enter the soil, they form triazonitrate 5 in the soil because they are going to combine with other elements. So, and this triazonitrate 5 are used by plants to also produce their protein. That's another way in which plants produce their protein. One by nitrogen fixation using bacteria, then the other one from triazonitrate 5 salts. So the next point tells us that animal ingest this protein and convert them to animal protein. So, but animal return this protein into the soil in form of wastes, especially as a urea when they urinate into the soil. So urea is a major component of urine, so it contains nitrogen. So then certain bacteria in the soil use the urea, convert the urea to ammonia, while others convert them to triazonitrate 5. You can see nitrogen keeps moving in nature. So nitrogen in protein is also returned to the soil as a result of decay. When plant and animal decay, after the death of animal, it enters the ground, they decay. Plants too, they enter the ground. When they die, they enter the ground and decay. So the protein in them are returned into the soil. Plants can then use the triazonitrate 5 from the two sources, that is in D and E above. That is as a result of the decay, the one that entered the soil as a result of the decay, and the one that entered the soil as a result of waste. So all these things can be used again by plants to form another protein. So nitrogen keeps moving in nature. So the next option here, G, tells us that certain bacteria take up oxygen from triazonitrate 5 in the soil to liberate nitrogen gas, which can be released back into the atmosphere. So the cycle is completed. So there's another assignment here for the students. the student is to use a simple annotated diagram, that is a diagram that is self-explanatory, that is well labeled, that it doesn't require any explanation again. It might not require any explanation again to describe the nitrogen cycle. So draw the diagram of a nitrogen cycle. Let's move to the compounds of nitrogen. We are starting with ammonia this time. The topic says nitrogen and its compounds. So we can't just discuss about nitrogen alone. Of course, we discuss the compounds of nitrogen. So the number one we want to discuss among them is ammonia. Ammonia, this is the hydride of nitrogen. The formula is NH3. It may be present in the atmosphere when nitrogenous matter decay in the absence of air. So it may be present in the air in the atmosphere. It's not a normal or natural component of air. Ammonia is not one of them. It is present when certain things happen in certain areas. So that is why if you pick a sample of air, you may not see ammonia there. And if you see ammonia there, usually it might be that there has been a decay of certain nitrogenous matter, whereby ammonia gas is being released in the atmosphere. So now let's look at laboratory preparation of ammonia gas. Ammonia, because it's also a gas, so that's why we call it ammonia gas. Ammonia is prepared in the laboratory, by heating a mixture of ammonium chloride and calcium hydroxide, which is also known as slaked lime. The equation is shown on the screen there, and the diagram for the reaction, for the preparation, is also shown there. So the two substances, calcium hydroxide, which is the slaked lime, and ammonium hydroxide, they are heated inside a round bottom flask. So, and pass through the drying tower, through the from the underneath. So the gas moved up and is collected by upward delivery. But this time it's not collected over water, but collected over quicklime, which is a drying agent, because the gas is a soluble gas. So you can see it is collected by upward delivery, but not over water, because the gas is also less dense than air. So one thing to take note in this preparation of ammonia using this method is that the calcium hydroxide is used. That is the reagent for the preparation is used because it is very cheap and it is not deliquescent like caustic alkalis, like sodium hydroxide. Because sodium hydroxide could have been used, but sodium hydroxide is deliquescent, that is, it quickly absorbs water. But calcium hydroxide is not deliquescent like the others. So that is the number one thing that we need to take note there. Then the function of the quicklime there, we have said it is serving as a drying agent. So let's take note of that. What about the preparation of ammonia on a large scale? That is industrial preparation of ammonia. That is done by Haber process. By reaction between hydrogen and nitrogen in the ratio 3:1. Hydrogen 3, 1 nitrogen. So for example, if you are using 100 liters of if you are using 100 liters of nitrogen, you will use 300 liters of nitrogen. So ratio 3:1 by volume. And the pressure for that reaction is 200 atmosphere and temperature of 500 degrees centigrade. So the mixture is passed over finely divided ion catalyst, that is broken, that is in a granulated form, or fine particles in powdered form. So the ammonia produced is then liquefied by cooling it and stored. So it is liquid ammonia. So that is the equation of reaction there, Haber process. Now, the properties of ammonia is a colorless gas but with a choking smell. Choking means that it can make somebody not to be able to breathe well again. The gas has a kind of, the smelling is not a pleasant one, and it can choke somebody. I've said that one earlier. If you use the method of the formula that was told the other time, you will discover that the gas will be less dense than air. The relative molecular mass of ammonia, which is NH3, is 17. Nitrogen is 14. Then 3 hydrogen. That's 17. 3 times 1, 3 plus 14, that's 17. So it's less than 32. It's less dense than here. And that is why the gas was collected by upward delivery. Upward delivery is the same thing as downward displacement. Downward displacement means that any air that is inside that container where the gas is being collected will be displaced downward, while the gas will be delivered upward. So upward delivery is the same thing as downward displacement. And on the other hand, downward delivery is the same thing as upward displacement. So kindly take note of that. Number 3 physical property that we have here is that it is very soluble in water. It forms aqueous ammonia, which is the same thing as ammonium hydroxide. Ammonia is an alkaline gas. It turns red litmus paper blue. Moist red litmus paper, it turns blue. Then number 5 is easily liquefied into a colorless liquid at ordinary temperature by compression. It can be liquefied. It has a boiling point of minus 77.7 degrees centigrade. And concentrated solution of ammonia is also known as 880 ammonia, because it has a density of 0.880 gram per cm cube. So these are the physical properties of ammonia gas. Let's go to the chemical properties. It burns readily in oxygen. So burning in oxygen to give water and nitrogen gas. Then another one is that it acts with excess air in the presence of platinum catalysts to produce brown fumes of nitrogen 4 oxide. So ammonia plus oxygen will give us water, that's steam, plus nitrogen 2 oxide, that's NO. But nitrogen 2 oxide is not stable in the presence of excess oxygen. That's why they say excess. So you have nitrogen 4 oxide being formed according to the second equation there under number 2, as you can see on the screen. In excess, ammonia first reduces chlorine to hydrogen chloride. You can see the first equation there under number 3. Ammonia plus chlorine gas giving us hydrogen chloride and nitrogen. The hydrogen chloride then reacts with the excess ammonia to form dense white fumes of ammonium chloride. So you can see there. So the third equation that you can see, that you are seeing there, is a combination of the 2 equations above. So when you combine the 2 equations above, it gives you the third one there. Can we look at it together? 2 ammonia plus 6 ammonia gives 8 ammonia. Then 3 moles of chlorine. So you have 3 moles of chlorine still there in the number 3. The 6 hydrogen chloride in equation 2 cancels out with the 6 hydrogen chloride in equation 1, because both of them, each of them are on different sides. The one in equation 1 is at the product side. The one in equation 2 is at the reactant side, so they can cancel out. Then you have left at the product side nitrogen gas and 6 moles of ammonium chloride. So what we are trying to say here is that ammonia reacts with chlorine gas to give us ammonium chloride and nitrogen gas. Now number 4, it also reduces heated copper 2 oxide to metallic copper. So this is one of the methods of preparing nitrogen gas that we discussed earlier in the laboratory. Then in number 5, ammonia reacts with carbon 4 oxide at a temperature of about 150 degrees centigrade and 150 atm to produce urea. This is a reaction where 2 inorganic compounds react to form an organic compound, because urea is an organic compound. That is the formula of urea there. That's NH2 twice CO. So that is that one. Then the number 6 chemical property that we look at here is that it decomposes reversibly at high temperature to yield nitrogen and hydrogen. There is no need of giving this equation again. It is the reversible aspect of the equation in Haber process for the preparation of ammonia. So we don't need to start writing this one again. Then the next point here says, as a base, ammonia reacts with acid to form ammonium salts. For example, it reacts with tetrazosulfate 6 acid, as you can see in the equation there, to give us ammonium tetrazosulfate 6. Number 8, aqueous ammonia precipitates insoluble metallic hydroxide from solutions of their salts. Precipitate, that is, it brings out the precipitate of these metals, of these metallic hydroxides. This particular reaction is used in qualitative analysis to test for some cations like lead, zinc, aluminium, copper, iron, and so on like that. So we are going to see some of them here. The first example that was given there in the equation there under that number 8, as you can see on the screen there, is lead. A lead-2 compound reacting with aqueous ammonia. Aqueous ammonia means ammonia dissolved in water. That's why you see ammonia plus water there. So reacting with aqueous ammonia to give us lead-2 hydroxide, which is a white gelatinous precipitate. So it gives us lead-2 hydroxide. That's the precipitate. So then, now let's move forward. Hydroxides of zinc, iron 2, iron 3, and copper 2 are also precipitated in a similar way, giving white dirty. Let's take them one after the other. There's no need of reading them through like that. You can see everything clearly on the screen. Now, the first one, zinc. As you can see the equation there, zinc reacting with aqueous ammonia. That OH, that 2OH, is the OH from aqueous ammonia. That is ammonia dissolved in water. So when zinc reacts with it, it will give us zinc hydroxide, which is a white gelatinous precipitate. In the case of iron 3, it reacts to give us a reddish brown precipitate. A reddish brown precipitate. The precipitate can be gelatinous sometimes, then depending on the reaction conditions. If it is copper 2, it gives us a blue precipitate. It gives us a blue precipitate. So, and usually a blue gelatinous precipitate. Gelatinous means it looks like a jelly. So if you are carrying out the reaction in the laboratory during qualitative analysis, you will see the thing looking like a jelly, even right from the test tube, without you even touching it. You will see it like a like a jelly. Now, the hydroxide of copper 2 and zinc. That of copper 2 and zinc. So, in excess ammonia, we form complex ions. So, if you are carrying out a qualitative analysis, if it is that of iron 3, in drops, you will see a reddish brown gelatinous precipitate is formed. In excess, more precipitate is formed, which means that the precipitate did not dissolve. But in the case of copper 2 and zinc, in the reaction that you can see there, the precipitate will dissolve by another chemical reaction to form complex ions. If it is copper, the precipitate dissolves to give a deep blue solution, and that is copper 2 tetraamine complex that you can see there. Copper 2 tetraamine complex. So, as you can see in the equation of reaction on the screen there, so that is the deep blue solution that you are seeing there. Then, in the case of zinc, the white gelatinous precipitate dissolves to give a colorless solution, which is zinc tetraamine complex, as you can see it in the equation there. So please take note of this when you are carrying out your qualitative analysis, and these are also part of the chemical properties of ammonia. Now, how do we test for ammonia? When you are testing for a particular substance, you need to look for some things to identify physically, to say, yes, I can see this one. Yes, because this thing has happened physically that you can see, then it is this particular thing. So ammonia is a colorless gas with choking smell. That you can use that one to identify, but it is not the only colorless gas that is choking smell, that has a choking smell. It's another thing that you will use to further know that it is ammonia is that it turns a damp or moist red litmus paper blue because it is a basic gas. Then another thing is that it forms a dense white films with conch HCl acid, conch hydrochloric acid, or even if it is hydrogen chloride. In fact, the reason for using conch hydrochloric acid is because conch hydrochloric acid usually gives out fumes of hydrogen chloride gas. So, and it is even the hydrogen chloride gas that easily reacts with ammonia gas to give us a dense white film of ammonium chloride. So all these things can be used to test for ammonia. So what about the uses of ammonia? It is used for manufacturing important chemicals like HNO3, that's triazonitrate 5 acid, also for making sodium carbonate by Solvay process. So in Solvay process, sodium carbonate is made and ammonia is one of the raw materials being used. Liquid ammonia is used in refrigerators as a cooling agent, like that. Then number 4, aqueous ammonia is used for softening temporary hard water. So for softening temporary hard water. Then it is used as a cleansing agent in laundries. Ammonia is used as a cleansing agent in laundry for removing stains. It is also used in the production of nylon and for making fertilizers, nitrogenous fertilizers like ammonium sulfate, ammonium nitrate, carbamide, and ammonium tetraoxophosphate 5. So ammonia is used can be used for making all these important chemical substances. So this is where we'll be stopping for now. We are going to continue on nitrogen and its compound in our next meeting. At that particular time, we'll be discussing other compounds of nitrogen. We'll be discussing other compounds of nitrogen because we still have some other compounds of nitrogen that has not been touched. So thank you once again for listening. Bye bye.